Hey everybody, welcome back to another video in this series. I apologize for the delay. It's summer around here, so we had summer vacation and I had to fight with the Python library to get it installed for today's video, but we sorted it out back from vacation and we're here to talk about materials data, and we're going to give an example of how you might access materials data from some of these repositories which we covered in our previous video. So the example we're going to cover today is for the materials project, and there's lots of other ones. I think later on in the series we'll probably do some dedicated ones for citronation, for aflow, for some of these other ones that are out there, but for today let's talk about materials project because it's one of the popular ones and it's got a good example because it has a nice API. So before we go ahead and do that, we need to go ahead and download some of the tools that allow us to use the API, and to do that we're going to need to install the pymatgen library, and this is where I got stuck. It was giving me all sorts of grief on my computer. I don't know why, but if you go here and you look at this installation tab, then it gives you some really great tips, and eventually I was able to get it working. So let's jump over there now. Okay, I'm going to go to my command to fire it up. I'm going to do this in Miniconda. I had to install it in Miniconda, which is just like a stripped down version of Anaconda because it was giving me beef with my regular one. Okay, now I created an environment to work out of. So an environment is just a place where you can store specific versions of the libraries and code that you're going to be using in Python. So I'm going to do conda activate my_pymatgen, which is what I called my library where I'm going to be working with pymatgen as examples. And then I'm going to open up Jupyter Notebook. Now, I don't typically love working in Jupyter. I way rather working in Spider personally, but this was just easier. It was giving me less problems. So I'm going to run it out of Jupyter Notebook. Okay, now before we're able to do this, we're going to need, since we're going to be using the API, which is this sort of API, think of it as a way to, like, you have this repository where all this data is stored, and you've got you as the user writing code. How do you go about accessing using code the data that's stored in this repository? You need some sort of handshake protocol, right? And that's what the API is. It's a way for you to access the data on there in a specific way so that your code knows what to ask for, and this is what you're asking for, right? So you can go ahead and do that. If you go ahead and come to this API button on Materials Project, you'll see that where you can generate yours. So mine is here. I've got it hidden because I'm screencasting this, but you'll be able to generate your own API key, which will be unique to you as a user. But that's the API key that I'm going to be using here, right? All right, so that said, let's see how we go about using this, okay? In this Jupyter Notebook, I've got a couple things. So first off, I'm going to start by declaring my API key. So I've got the string representing my API key here hidden under the box, and I stored into the variable Sparks API. So that's just a string of numbers and letters representing my unique API key. All right, now pymatgen can do all sorts of really cool stuff, right? So if nothing else, like forget like all the data aspect of it, it's just got cool things about the different things in the periodic table, right? So we're going to do import pymatgen.core as mg, right? So we've got pymatgen.core, and then you can do things like, we can say that for the element silicon, we're going to create a variable called si, and we can do mg.element, so it's got this method for element, and we can just send it the string for silicon, and all of a sudden, stored in the value of silicon, we can do all sorts of cool things. We can print, say, silicon has the atomic mass of, we can call that element, right, that object, and now we can pull up its attribute atomic_mass, and it's got the correct atomic mass stored for it. So it's just a useful material science library. There's so much more than what we're going to cover in today's video, because today we're focusing mostly on the API, but just to point out that it can do a ton of really cool things, right? This is a very simple example, but there's tons more there, right? Now, when you want to go about gathering data, there's different ways that you could do it. One thing you could do, we could come over here to my Materials Project website, and one way to go about gathering data would be to just like point and click it and access it via the graphical user interface of the website. That's not going to be a great idea because it's going to be slow, right? Let's say that I want to go and I want to pull up, like they suggest here, NA-O. I'm going to search for things in the NAO system. And it's going to go ahead and it's going to pull up any entries it has that are in that system. So NaO2, Na2O2, Na2O. For any one of these, it has a materials project ID number, MPID. And then it's giving you some information right off the bat right here. But for any one of these, you could click on it and you could see more information. You could see the sort of stuff that it has. So one way to go about accessing these databases, this is the wrong way to do it, would be to just individually click these things, and maybe you're after the density and you could say, aha, there it is, and you could write down 2.35 or copy it. Like that would be a really slow way to do it, okay? So there's better ways to do that. You'll notice up here, check this out, it says materialsproject.org/materials /mp-2352. Well, that's the unique ID number for this entry. So it's in the URL, right? So that would be one way you could access them. So that's one we're going to show you here, right? You could go ahead and you could do this. We're going to copy and paste this over here. I'm going to hide my key, but you would use your key, right? So it's materialsproject.org/rest/v2/materials/ you put in the materials project ID number for whatever you wanted to get /vasp /AP_key, and then over here where it's missing, it would be you're putting your key, your individual API key, and out would come this big blob. So all this stuff that gets responded, this is a JSON file, which works a lot like a Python dictionary, which is going to make our life easy. So it would return all that. So one way to go about programmatically accessing this would be to have something that generates this URL corresponding to whatever compound you're interested in, and then you gather all of this data. Now, in the real world, you probably don't need all of this data, right? You don't need like the piezo null, this dielectric null, this deprecator. Like, you don't need any of that stuff. You probably just needed the density. And so why pull everything if you only need just the density, especially if you're doing this for many, many compounds? Fortunately, the API makes it really easy to do that, okay? But this is one way. So you can either go in person to the website and grab it, not great. You can pull it up by the URL, that's not great, but it would technically work. Or you can start making requests, right? For example, here, I can do this programmatically. Instead of actually going over to my browser and pasting that, I can use the requests, right? Library, I'm going to do import requests, and I'm going to say that some response is equal to requests.get. So this allows me to actually get something, right? It's gonna send it, so I don't have to go to the browser. It's gonna do it automatically. I'm gonna do get HTTPS. I'm gonna send that exact same thing as before, VASP, and then I'm gonna send it my API key. So the API key is now stored in a dictionary where the keyword is API_key, and I'm sending it my individual key, which was again just a string. And with this now address, this URL, and the API that I'm sending it to, it can get this response. Yeah, and sure enough, we're going to print the response.txt, and it's the exact same thing that you saw before. So it's still returning too much information, but at least this time we did it in a programmatic manner. It was really easy to go about having Python run this. We didn't have to like manually copy and paste this over to our browser and work with it, because we were able to use requests.get. So we're getting closer to maybe what we're after. Okay, let's look at some other ways to do it. The best way to do it is to use the API for this, right? Now, to do that, there's something called the mapidoc, which is sort of like the architecture. It's the way that the API is organized. So let's go ahead and jump over to that. There's this link here to the GitHub for Materials Project's mapidoc. And this shows you the structure of all the information that's held there. You sort of saw a glimpse of it. You saw all the types of information that's stored here, right? You can see that number of elements, space group, Hubbards, energy above whole. This has the information on all of that stuff, right? So it's a GitHub, and you can look through it. Very actively maintained here. And if you look at like under materials, for example, you could say, look at all the stuff like density and every one of these. This is the sort of architecture. So under materials, there'd be something under density, and you can read, what these are. They should include the units on this, so you know what the density of that is. So we could actually submit an issue and say, hey, add units to this if we wanted to. Okay. All right. So that's how that is going to work. That's what the mapidoc is. And then the tool for actually accessing the rester, you're going to want to use MPRester, right? Now, MPRester is awesome. This is a really cool tool that's going to help us be able to access the API in a really simple way, right? So it says MPRester, it says, this module provides classes to interface with the Materials Project REST API version 2 in order to enable the creation of data structures and pymatgen objects using the Materials Project data, right? And they make it really easy. So this MPRester has all this really cool, these really cool methods and attributes associated with it. So for example, it has things like get cohesive energy, right? This built-in attribute that's going to allow us to using this tool, access just the cohesive energy from all this big blob of information that came up from before, right? It's going to know how to just grab energy per atom or whatever else, right? So that's the MPRester. So let's go ahead and try it out. We're going to say from pymatgen.ext.matproj, we're going to import MPRester, okay? Then we're going to do with MPRester as MPR, just so we don't have to type the whole thing out. We're just going to call it MPR. Let's go ahead and do this. We're going to say, we want to grab, using pymatgen, all of the compounds that have tantalum carbide as the formula. The exact formula is going to be tantalum carbide. So to do that, we're gonna print, the exact number of matches are we're going to go MPR, and then it has this get materials IDs. And again, if you couldn't remember the syntax for what to do there, you could hop over here and we could do Control F, and we could do get materials, right, IDs, and we could look for the one like right here, and it says, okay, get materials IDs. The input, it's looking for chemical system formula, right? Get all material IDs for a formula or a chemical system. So great, that's what we do here. We send it a string for our chemical formula, tantalum carbide, and it's going to return anything that is exactly tantalum carbide, right? Meanwhile, you could ask for all the compounds in the entire system. So this is now things not just a 1-to-1 ratio. Maybe it's 2 tantalums or 2 carbons or whatever else, right? So this is going to be slightly different. We're going to do MPR. This time it's going to be get materials IDs, but instead of sending it an exact formula, we're going to do something tantalum-carbon. That means that it's in the chemical system. That's the sort of notation that Materials Project uses. So that's going to be obviously more entries. When we run this box, sure enough, we see that the exact number of tantalum carbide formulas in their database are 1, 2, 3, 4. There are 4 Materials Project IDs corresponding to tantalum carbide. Now, maybe they're different space groups or different crystal systems, I don't know, but there's 4 that have the formula TAC, right? And then all the systems in the tantalum carbide system, there's a whole bunch, right? There's all these things, right? I haven't counted them up, but there's a whole bunch of those, okay? Those are all the ones in the system. So there's our first example of actually we were able to grab data in a very efficient manner using the MPRester tool, right? So in this case, we were just grabbing the IDs, but you could imagine that we could grab lots of information, right? Because this MPRester has lots of different methods associated with it for grabbing different things, get reactions, get stability, whatever it may be that we're after. So let's show you some more examples of this, right? Okay, how about this one? Okay, this time, let's say that you know the Materials Project ID, and now you want to pull something from that. Okay, so this time, again, we're going to do with MPRester. I'm sending it my API key. I don't know if you have to do that every time. I don't think you do, actually. I think I already did it above, so it should be fine. But in any case, it doesn't hurt it. With MPRester, I'm sending it my API key as MPR. Okay, this time we're going to store it into the structure. A variable called structure is going to be equal to mpr.getStructure by material ID. So the method is getStructure by material ID, and you can guess that the input it's going to want is a string representing the Materials Project ID. So if we send it 1086, which was, I think, yeah, this very first one for tantalum carbide, now it's going to tell us what structure it is. Great. Okay, so we can go ahead, and when we run that, it's going to tell us what structure it is. Okay, and then we also, so it says the structure right here. Here's our structure. It's saying that it shows you that the ABC lattice parameters are all equal, saying what the angles are. Okay. And then you can say, let's do the same thing for cohesive energy. So we're going to make a variable called cohesive energy. We're going to do MPR, and then we're going to use the method get cohesive energy. Send it the exact same thing. It's going to return that thing back. So that's the sort of tools that MPR makes available for you, which is pretty rad. So it can also do some really cool things. Like, check this one out. Let's say that you had a sieve card. Maybe you were using the Crystallographic Open Database or the ICSD or something like that. So you know what the structure of a compound is, but you don't know what its other properties are. Like maybe Materials Project has done DFT calculations for other properties, and you'd like to check some of those. Well, you can actually find it by inputting the sieve card. So here's an example. We're going to import OS. That allows me just to grab from my file location, basically. We're going to do MPR equals MPRester with the Sparks API. And then we're going to do sieve file is equal to os.path.join, and I'm going to say that the name in wherever we're operating out of right now, that there's a file, a sieve file called lab6. And sure enough, if I come over here to where we're working, we're in this API example, I've put this lab6 sieve file. You could name that anything you wanted, though. It could be named, whatever, and it would still work. I've given it the name, the correct name of whatever it's called, and then I say, okay, we're going to say that the data is now equal to MPR. We're going to use the method find structure. We're going to send it that sieve file, right? The information stored in that sieve file, we're going to send it, and then it's going to find it. And sure enough, when we run it, it's able to find, oh, we have that structure associated with this Materials Project ID. So then you could use that ID if you wanted to pull up, whatever else you wanted, stability, whatever. Okay. Now, one of the important things that if you're doing materials informatics you might want to do is you might want to look at certain sets of data. Like, it's not like you want to grab like everything in the Materials Project. It's massive for one thing. You just want to grab things in a certain system, maybe. Maybe you want to grab like all of the, for example here, what if we want to grab the carbides that contain either tantalum, niobium, or tungsten? So we want to grab tantalum carbides, niobium carbides, or tungsten carbides. How do we do that, right? So fortunately, there is this query method. So in the MPRester, you have this query method, which makes your life so easy. Query uses something called MongoDB's query syntax. I'll show you an example of that in a minute. It's pretty straightforward. And then anytime that you use the query method, right, so mpr.query, what it's going to expect inside of there is a criteria and then the properties. So it says, okay, when you want to query, when you grab certain things, what's the criteria that you're using? And then what are the properties that you want to get with that query, right? So let's do an example, right? How about this one right here? So we're going to do MPR equals MPRester using my API. So here's a few. You could say mpr.query. We could send it, the criteria is we want everything with the chemical formula SiO2, right? And then the comma, the second one, these are the properties. We want its material IDs and we want the densities, okay? That would be one way to do it. And when you run that, let's go ahead and run that one. We'll comment this other one out. And it's going to return everything that is SiO2, and it's going to return the material ID and the density. So here's all the things that are SiO2, silica, in the database, and there's a whole bunch of them, right? And it's returning the MPID and the density, right? And now another thing we could do, let's try this one. You could do npr.query and then asterisk 03. So that's called wildcard notation. It's something that's built into materials project that allows us to basically use, it's like a hotkey. It's doing it faster. You're saying anything as long as it's oxygen 3. So in the chemical formula, this is going to return anything that has an element in both 1-to-1 ratio, and then 3 oxygens. And it's going to return the pretty formula, whatever that category is, pretty formula, and the material ID. So let's go ahead and run that one. It's taken its sweet time to think. It must be going a long time. There's going to be a lot of perovskites, obviously, in the database, so it's not surprising it's taking a long time. Okay? And then down here, if we scroll down, here they are, and there's going to be, you know, a gazillion of them. It showed you this progress bar as it was working along. It automatically, when you request something large like that, it automatically breaks it up into chunks behind the scenes. You don't have to worry about it, which is nice, and then it goes about returning them. So sure enough, it tells us what the pretty formula is, and sure, it's calcium, iron, O3, barium, silicon, O3, barium, germanium, O3, right? So on and on like that. Let's do one more over here. This time, instead of asking for all the perovskites, basically in the database, let's ask for everything. The criteria is this, right? So the criteria, we're going to send it a dictionary, and the dictionary has the keyword of ChemSys, right? So in the chemical system, and then the values are O-SI. So we're going to ask for everything in the chemical system of silicon and oxygen, and we're going to ask it to return the material ID. And here we go. It's returning. All of these should be silicates, SiO somethings, right? Something in the SiO system. So those are a couple examples of query. Now we haven't done any MongoDB query syntax yet. I'll show you that in just a moment. In fact, here's one from a video that I saw John Dagdalen put together that I was putting together as I followed this. You can see it here in this link. I'll put links to this in the video description. But I like this one. Here's how they started. So first off, they imported matplotlib.pyplot as PLT because we're going to plot something. We're going to do this %matplotlib inline. That's going to let us actually show the plot here in the Jupyter Notebook. Now we're going to do with MPRester, with my API key, as MPR. We're going to create something called entries, right? So this variable or object will be entries. This is going to be equal to mpr.query. So again, anytime we do query, you're thinking constraints and properties. So the constraints are everything in the tantalum carbide system, right? And then the properties we want it to send back is, well, the material ID and also the space group dot crystal system. Now, how do we know that it was space group dot crystal system? Again, if you go back to the mapidoc, come here under materials, if we were to scroll down to space group, right, there would be a dot crystal system, right? So that it's helpful that if you understand the mapidoc architecture, right, you knew that we could have done space group dot number or space group dot point group, and it would have also worked. So that's why that's helpful to understand how this architecture works. Okay, so it's going to return the crystal system, whether it's cubic or hexagonal or trigonal or rhombohedral or whatever, right? That's what this is going to return for us for every compound in the tantalum carbide system. Okay, so let's go ahead. So when you run that, all those would be stored in this variable, this object entries, right? And then we're going to do this. We're going to say that the systems themselves, right? Because if we want to actually plot how many of them correspond to different values, we're going to do something called list comprehension. Those that are familiar with Python are familiar with this. It's basically like a for loop wrapped up into one little line. We're going to say for every entry in the variable entries, right? So you have all these different systems, right? Every different compound in the tantalum carbide system. you have all this information stored in that dictionary. You've got the material ID, and you've got the space group.crystal system stored there. So for each one of those, we want to return the entry, right, for entry and entry. So for each one of these entries, line by line, we want to return the space group.crystal system and put it in this variable systems, okay? Now, let's go ahead and count those up. We do that by starting an empty dictionary for counts, and then for each system in systems, so we're going to go one by one through all these crystal systems that we just stored in there, and we're going to say, if the system is in counts, right, if it's already there, then just add 1 to that score. We're going to say that counts in the system value, in the system keyword, is going to be plus or equal to 1. So that's just saying add 1 to the previous value. Else, we're going to say that counts in the system position is equal to 1. So if it's not in there yet, give it a single value, and otherwise add it up. So this will go one by one through all of the entries in our tantalum carbide system. And we looked up previously, there was, a number, all these ones. So however many there are, there's 10 or 20 or something. It's going to go one by one through them, and it's going to be counting up what the crystal systems are for them. And then at the end, we can now use pyplot, which we brought in, pyplot to do a bar plot, where we're going to plot the total number of them, right? We're going to do the range of the length of counts, and we're going to actually plot the values. So counts.values. And then for the X marks, you can actually put the names, right, of them. So we're going to do the range length of counts, and we're going to do our key there's up to 7 space groups, up to potentially having 7 crystal systems, So for key and counts.keys, those will be the labels. And sure enough, we see that there are 4 in the cubic system, there are 3 in the hexagonal system, 3 in the trigonal system. So this is an example of how we've now used the API to query under very specific conditions, like how to pull out real meaningful data that you might want to use for machine learning, and then start to organize it and plot it. So nice example there from John Dagdalen. How about this one from WinHouseWin? I like this one. So they're going to bring in, it says from pymatgen.analysis.phase diagram. I told you it can do a whole lot more than just like atomic numbers. It can do phase diagrams and all sorts of cool things. We're going to import phase diagram and PD plotter, and then math, right? So again, we have to use the material MPRester. So we're going to do MPR equals MPRester with my API. Then the example he has here, he's looking in the calcium oxide system. He's going to want to grab all the entries that belong to the calcium oxide system. So he says entries equals MPR.get entries in chemical system, and he's sending it a list of the chemicals, the elements basically. Says if you are in this list of elements that I send you, calcium and oxygen. And again, if you couldn't remember that this was a list, you could find it by just coming here and then searching for, what is it? Get entries in ChemSys. So we're going to do entries in ChemSys, and sure enough it says, exactly, helper method to get a list of entries, for example, elements, blah, blah. It tells you exactly how to use it. Okay, so now you've got all the entries that are in the calcium oxide system, and then you can do cool stuff. You can say PD equals phase diagram of entries. So all those entries, you can just use this function called phase diagram, and it will generate a phase diagram, and then you can plot them. So this is a pretty cool tool. You can see that it generates this phase diagram for the binary system between calcium and oxygen. And then what's really cool is it's interactive, right? You can hover over this and get it to interact with you in pretty cool ways. Like for that data point, pure calcium, it tells you what its materials project ID is, and it also telling you the energy above the hole. Like, so some of these things are not stable. Like this version of oxygen is not stable relative to that version of oxygen. Or let's come over here and look at a different one, right? Down here at the bottom, the calcium oxide that we know and love is green, showing it's the most stable one. But this one just above it, there's a different version, probably a different crystal structure, right? Which is not on the convex hole. It's actually slightly higher in energy. So really, really cool tool for visualizing doing this. Obviously, we can do the same thing, but now for our system. Let's say that our entries, we want to do MPR.get entries in the chemical system. Let's say we want to look at everything in the niobium tantalum carbide system. So it's going to pull in all of those. Now it's a ternary, and when you do the exact same thing, it's able to generate this really cool ternary plot. So again, now you are between niobium, tantalum, and carbon, and for each one of these you can hover over it and see, oh, that thing is either favorable, stable, or it's not stable, or maybe it's slightly metastable. Maybe that's this orange one, it's only just a little bit above the hole maybe, and so that becomes something of interest that maybe you could access. So really, really cool stuff that it's able to grab using this API. Here's another one from WinHouseWin. This one actually uses some MongoDB syntax, right? So this one, let's say that you're trying to grab any compound that contains oxygen, but it must also contain either lithium, sodium, or potassium. So here's how that goes about doing it. So again, anytime that you do MPR.query, you're going to send it a criteria and a properties. So just to make it cleaner, he actually called it criteria equals criteria and properties equal props. And then he defines those up above. Like the properties that he wanted to bring, he wants the structure, he wants the material ID, he wants the pretty formula, he wants the energy above the hole, he wants the band gap and the band structure, right? So he's going to grab all those 5-6 things. Now what's the criteria? Well, there's a bunch of criteria. He says, okay, when you do this, it's a dictionary. So this whole thing's a dictionary, and it's made up of dictionaries, right? So the first entry, he says, okay, for elements, that's the keyword, he's using a dictionary right here. And inside that dictionary, it's made up of a keyword, which is MongoDB. So it's this $in. So the MongoDB query syntax starts with that $. So this basically says, as long as one of these elements is in the formula, it's okay. So $in, meaning this must be in the formula, and the values, so this is the keyword inside this dictionary within the dictionary. The keyword is $in, meaning it has to be in that formula. And then he says the elements that are acceptable to be in the formula. Then he has another one, so he has 2 entries in terms of chemistry, not just that it has to contain at least lithium, sodium, or potassium, but now he's got a second entry, so a second dictionary entry. This time the keyword is $all, meaning every single compound must have whatever this is, the value in the dictionary, and that's oxygen. So these must be oxides, and they must be oxides of either lithium or sodium or potassium. So pretty slick how you can do that. Then he's got some other things. He says, okay, another criteria, I only want you to return ternary compounds. We do that by using number of elements, n elements keyword equals 3. Now again, it'll take a little bit of practice to learn what these things are. Like remember, if we go way back up here, we saw this. N elements was, where was it? Right, elements, right? This was one of the things that got returned in that mega list. So it's just one of those things there. With a little bit of work, you'll start to remember these things, right? But the number of elements was 3. He says, I only want you to return things, right here, check this one out. It says, so the keyword is ICSD ID. So the ICSD is a crystal structure database, right? And the materials project has some of their compounds associated with these ICSDs, right? So if we pull up this one, for example, if it has an ICSD number, right, it might be included here. But some of them won't have that. So what he's saying here in his code, he's saying, only return to me things that in the ICSD ID category you have this MongoDB syntax. And what he's got here, again, it's a dictionary instead of a dictionary, and this dictionary's keyword says $GTE. That means greater than or equal to some number. So if it didn't have an ICSD associated with it, they wouldn't put a number there, it'd just be not a number. So he's saying only return to me things that have a number by basically saying greater than 0. Okay, so that's a clever way of only returning things that are correlated with an ICSD structure, okay, which is nice because those are experimentally determined. And then you've got this other keyword, E above hole, that's energy above the convex hole, right? So it's a measure of how stable something is. And the dictionary there, the MongoDB syntax is $LTE. You can guess what that means. If this is GTE is greater than or equal, then this is going to be less than or equal to 0.01. So that's something that you're only returning things that have, they're within 10 milli electron volts, right? 0.01, that's 10 milli electron volts of the convex hole. So you're only returning things that are either stable or close to stable, not things that are far from equilibrium. And then you've got this one here, anonymous formula, and the keyword for that is anonymous formula, and then the entries here, you've got a bunch of keywords like the A position needs to be 1, the B position needs to be 1, the C needs to be 1. So these need to be ABO3 or ABX3 or ABC3 type compounds with 2 cations, 1 anion, or at least that formula architecture, 1, 1 to 3. And then lastly, that the band gap needs to be greater than 1. So for whatever reason, this is the search criteria. You and your research might have something a little bit different, but this is the idea behind it. You can set up very specific query criteria, save it as a criteria, and then do your query and it will pull it up. And so in this case, when you run it, I think it actually returns, he prints, tell me how many entries fit this criteria, and it's something like 52. And so for he's going to go one by one through those, printing, okay, tell me the pretty formula, tell me the band gap, then actually spit out that file. But then he does break, so after the very first one it stops, and you can see here that there was 52 in the database that fit that criteria, and the first one is this potassium arsenic oxide, shows you the band gap, and then it starts going ham, showing you everything about that structure. It tells you all the different atomic positions, all that jazz that it asked for, right? Because remember, he asked for a number of things. He asked for the structure, the material ID, the pretty formula, energy above hole, band gap, band structure, all that stuff got returned, and then it broke the formula. So pretty cool stuff. There's obviously way more that you can do. This is not meant to be exhaustive. I am not an API, master for anything, let alone certainly not materials project. But even a noob like me, without my grad students' help, can sort of bumble my way through this. So you guys, as materials informatics researchers, can get pretty good at this, I think, and actually start accessing the data in this database to do really cool machine learning. So with that said, we're going to jump into our next one, which is going to be the tasks and the types of different tasks and types associated with different machine learning types. Okay, see you in the next video.